sklearnutilsextmath. Description: the sklearnutilsextmath module provides optimized numerical routines for common operations in machine learning, particularly for working with matrices and vectors. These routines often leverage efficient implementations in libraries like BLAS and LAPACK. Inputs. Input matrices or vectors. These are typically NumPy arrays that represent data, features, or model parameters. Optional parameters. These can include parameters like thresholds, regularization strengths, or other settings specific to the function. Outputs. Computed results. The outputs depend on the specific function but typically involve transformed matrices, vectors, or other calculated values. Steps. Matrix vector transformations. Functions may perform operations like matrix multiplication, singular value decomposition (SVD), or eigenvalue decomposition. Optimization. Some functions leverage techniques like QR factorization or Kolsky decomposition for efficient computation. Regularization. Functions like safesparse and logsumMakesUp can incorporate regularization to handle sparse data or prevent numerical issues. Metrics. Runtime performance. The speed of computations is often measured, particularly when comparing different implementations or algorithms. Accuracy. For operations like SVD, the accuracy of the results can be evaluated against known values or theoretical expectations. Numerical stability measures are taken to ensure that calculations are numerically stable and avoid issues like overflow or underflow. Visualization plots. Matrix visualizations. Visualizations like heat maps or dendrograms can be used to analyze the structure of matrices, especially for dimensionality reduction or clustering tasks. Scatter plots. Plots can show the relationships between transformed data points to understand the effects of operations like PCA or MDS. Fine-tune parameters. Regularization strength. This parameter can be adjusted to control the amount of regularization applied, affecting stability and generalization. Thresholds. Some functions use thresholds to filter values or determine convergence criteria, which can be fine-tuned to optimize performance. Numerical precision. The precision of calculations can be adjusted for specific applications, trading off speed for accuracy. Uncertainty methods. Bootstrap resampling. For methods like SVD, uncertainty can be estimated by repeatedly sampling the data and computing the decomposition multiple times. Confidence intervals. Based on resampling or other statistical techniques, confidence intervals can be calculated to quantify the uncertainty in the results. Challenges and fixes. Challenge 1. Handling sparse data. Sample use case. Working with datasets containing many zeros can lead to inefficient computations if not handled properly. Fixes. The module provides functions like safesparse that efficiently handle sparse matrices, preventing unnecessary operations on zero values. Challenge 2. Numerical stability. Sample use case calculations involving very large or very small numbers can lead to overflow or underflow errors. Fixes. Functions like logsumMakesUp use logarithmic transformations to improve numerical stability, particularly when dealing with sums of exponentials. Challenge 3. Memory efficiency. Sample use case working with large matrices can lead to excessive memory usage, especially when performing operations like matrix multiplication. Fixes. Some functions, like sparse are optimized to work with sparse matrices, reducing memory requirements.